Okay. Hi, everybody. Thank you for joining us today. My name is Aisha, and I am one of your Solid State Circuit Society staff members. The topic of today's webinar is Design Exciting Chips in the Classroom, presented by Bora, Nikolic. Attendees of this webinar have the opportunity to earn a certificate of participation for attending this webinar. I will put a link in the chat box with instructions on how to obtain the certificate. Please use the Q&A on your dashboard to ask any questions. The Q&A can be found in the bottom right corner where the three dots are. I now invite our SSCS committees, Young Excellence and Women in Circuits, to introduce our speakers and give a few welcoming remarks.
Hey, Aisha, thank you very much. My name is Farhana Sheikh, and I am co-chair of the Women in Circuits Committee for Solid State Circuit Society. And joining me is Taeyong Kim, who is representing young professionals and also leading the WYE webinars. So this is a joint webinar from both committees. And we're very happy to have Bora Nikolic here, who's going to talk about some very exciting things that he's been doing in the classroom. And he has a cohort of students that are going to help with the presentation. I'd like to first introduce Bora. He's a professor of electrical engineering and computer science at the University of California at Berkeley, and he holds the National Semiconductor Distinguished Professorship in Engineering. He co-directs the Specialized Computing Ecosystems Lab and the Berkeley Wireless Research Center. He received his Diploma of Engineering and Master's degree in Electrical Engineering from the University of Belgrade, Serbia in 1992 and 1994, respectively, and then PhD degree from University of California, Davis in 1999. Since then, he joined Berkeley as a professor, and his research includes digital and analog integrated circuit design, VLSI implementation of communications, and signal processing algorithms. He is a co-author of the book that everybody knows, Digital Integrated Circuits, A Design Perspective, a very, very useful book if you haven't read it. He's received the Best Paper Awards at IEEE solid state conferences such as ISSCC, VLSI Symposium, Europe SCirc, and then CICC. He has also been a distinguished lecturer for the IEEE Solid State Circuit Society and has been the technical program chair for VLSI Symposium and general chair of the conference just recently in 2024. Please welcome Bora Nikolic. And we're going to go on to, before we do the presentation, we're going to actually do a quick review of women in circuits. So our goal is to have 30% representation in membership, SSCS conferences, and committees, and the administration committee as well. Next slide, please. So we have a number of events that we do at every conference that's sponsored by SSCS, including just recently the ISSC conference, where we also provided family care and mentoring events. And we also sponsored a technical evening panel. And you can see that we're going to have events at every single conference this year, all the way through to November. Next slide, please. There's some new things coming online, and students, please take note of this. And also young professionals, we are actually doing some student outreach, and we're going to have a contest that is going to be launching in the second half of this year, where we're going to invite proposals on how to do awareness and outreach in geographic regions where there's very little awareness of semiconductors. And we are going to be sponsoring some travel grants and honorarium to people who can go and talk to people in their local language in those regions, and then come back with a report outlining a program that they would like to implement in that region to increase education and awareness of semiconductors and circuits. Next slide, please.
Yeah, here is my stages. So my name is Taeyong, and one of the WYE committee member, which is webinar for Young Excellence to support the SSCS Young Professional member. Here's a select IEEE SSCS Young Professional and Student benefit. One is the resource center. It's the technical. We provide the technical tutorial and the short courses and webinars, and also the distinguished lectures. And there's a student travel grant and postdoctoral achievement award, comparable award stuff, and up to the 1,500 young leadership volunteer travel award for the SSCS conferences. And like you can be a YP leader in your local SSCS sections once you apply that. And SSCS Young Professional Networking event for multiple SSCS sponsored conferences and new mentoring program through the SSCS website. You can use the SSCS mentoring.chronos.com. Here's I create this webinar for Young Excellence. Is a webinar structure dedicated to YP members to get more the insight in the industrial design practice, and then collect the career advice and represent the research idea and beyond. We have 9 community members for WYE, and we have a YouTube playlist for the previous webinar series. And you can use the QR code to use the or use the keyword as SSCS or WYE, then you can find it. We can give a cue to the presenter, Professor Bora Nikolic. Bora, it's your stages. You can share it.
All right, thank you very much for introducing me, and thank you, young professionals and women in circuits for inviting me to present today. I will have 3 co-presenters who will be mostly helping demonstrate some interesting stuff straight live from the lab, and perhaps answer some questions particularly about their experiences in participating in these interesting experiences that we have had. So I'd like to introduce Lucy Ravina and Ethan Gao, who are right now on your screens and in the lab. Lucy is a 5th-year master's student at UC Berkeley, and Ethan is a graduating undergraduate senior. I'd also like to introduce Anse Smolbach, who graduated from Berkeley and is a 1st-year graduate student at MIT now. She is right there also with her video on for the moment. Okay, so I'll get going and talk about some of the stuff that we have done. We have done a lot more than can be presented in about an hour, which what I was targeting, maybe a little bit more than an hour. I'll make a few pauses to let people ask questions, and then we'll try to answer them. But the idea here is to try to show what we have done, which not very many people are familiar with. Although we had several hundred students go through this exercise of designing chips as a part of a semester-long course. So let's get into it. This is a motivational picture. This is a picture that was taken at the end of the class last spring 2024, when we celebrated a successful tape-out. The tape-out was done by about actually precisely 68 students, and there were 2 faculty involved with that, and there was 7 teaching assistants who were helping out get these chips out. Not everybody is in the picture because this was done, this celebration was done during the final exams, but most of them made it in. It is quite an impressive number to get to that level where mostly undergraduate students conceptualize, design, and send out for fabrication a chip that is that ends up being functional a few months later after it comes to the fab, from the fab. So how did we get here? Well, it was not the most straightforward path. Like many people have figured out, the popularity of hardware design has been going down over the years. So a long time ago, maybe some 20 to 25 years ago, UC Berkeley had a very vibrant program in chip design, in IC design, under very different conditions in the industry. And very many students were taking our classes. We had two classes, one on digital circuits, one on digital systems, and then several analog classes. But just for the reference, digital circuits and digital systems classes were taught in every semester, and about 400 students per year were taking them. Many of them entered the industry, and many of them are the people who are practicing this design in the field. But the interest started going down over the years. There are many reasons for that. IC design became harder. There are many other opportunities that had an easier path to a career, and perhaps with a better pay. With just a few different courses in computer science or software engineering, you could end up on a path that would pay you better. And our students know how to recognize those opportunities, and they essentially went over and started flooding those classes. As a result, our chip design classes or digital circuits and systems classes started becoming less interesting. I think we hit the bottom around 2017, 2018, where during the entire year, the course was offered twice. First the class, we stopped having two classes. We merged that into only one class because there was no point of teaching two classes if people are not that interested in that. And then we had a number of first-year students, 18 first-year grad students took the class, and then a total of 23 undergrads. At that point, we were essentially at the brink of cutting this down to one offering per year and eventually getting out of this business. But at the same time, a number of companies started coming to us and said, we need graduates, and we want to pay them well. We want to pay them market rates, and this is an exciting career. Please help us do something about this. So we decided to help out with that. At the same time, we became aware of this widespread issue. This is a chart that I grabbed from Raja Kaduri, who was at that time at Intel, running the GPU business, showing what has been happening over the years, over the past 50-ish years or so, where popularity in programs that offer both EE and CS, well, almost everybody was in EE, and CS almost did not exist in the 60s. Fortunes completely reverted, and we have now more than 90% of students who are in ECS are in CS, and less than 10% are in electrical engineering. Traditionally, your chip designers, people who you would expect to be practicing this chip design, are getting to be pretty senior. Those are the people who graduated around my age and before me, and when there were 50% of the population, there was a lot of excitement. The idea here is the new chip designers will have to come mostly with CS backgrounds, and people who have strong computer science skills make really good chip designers. I promise you that. I've seen that from our graduate students. So one of the things that we wanted to do is to make chip design attractive to CS majors. We did that by making this attractive to the program of designing chips, attractive to CS students, also by industry being aware that they do need to hire and that these jobs are really attractive. We got many more students come our way. Well, first, they were a little bit hesitant. A few brave ones tried out, but now we have many more students interested in getting into hardware design than we can serve them. We are, in order to get into to be a solid hardware designer, you need to have some lab experience, and we are limited by the lab capacity, and what we can fit in our labs are about 250 students per year. This is quite exciting. And one of the big things that has contributed to this has been the introduction of chip designs in semester-long classes. So this seminar will talk about what we did with that and how that class evolved over the past 5 years, and how we started with something quite ambitious but yet modest, to evolve to designing complete systems on a chip on a fairly advanced Intel silicon. Now, designing chips in a class has been something that was going on since through the 80s and 90s of the last century. Well, most young professionals were probably not even born back then, but this was something that really reverberated through the both industry and academia when this happened. There was quite a bit of a revolution then when Mead and Conway published their book, and Lynn Conway offered the VLSI design course at MIT in 1978. What they did is they designed several, this class of young professionals back then, designed several interesting chips and sent them for fabrication. They were fabricated and they came back, and that became something that was very popular throughout the academia, mostly in the US, but also around the world, in the 80s and 90s, and lived through maybe early 2000s. Even in Berkeley, some of the people whose names you may recognize from some textbooks, David Hodges, Randy Katz, and Dave Patterson, offered a series classes in which students would design a reduced instruction set computer by taking 3 classes and by sending it out in 1.2 to 2 micron CMOS technology back then in the 80s. And I at some point I used to look like this young professional or a student in the picture. As a first-year graduate student, I designed a chip like that in the course of 3 quarters at UC Davis. I designed in one semester we did a schematic. In 1 quarter we did a schematic. In the 2nd quarter I did a layout. Then during the spring break, before the spring break, it was sent out for fabrication and came back during the spring quarter, and I tested it and it worked, and I even published a paper about it back then. I was very proud of myself. And that was something that left a lasting experience that lasted me throughout my career. But these classes disappeared. There are many reasons for that. Chip design became a lot more complicated. Not something that is easy to pull off in the course of a semester. Chip fabrication became more expensive, and NSF killed the idea of funding these chips. My chip cost $500, and it was paid by the NSF to do it nominally. 2 students would share a $500 chip, and but I was the odd one in the class, so I got the whole chip to myself. And then also fabrication times got a lot longer, and it became impractical to do something that is relevant in the course of 1 or 2 semesters or 2 or 3 quarters, and get these chips designed, sent out for fabrication and tested. But there are people who don't believe in that, and my colleague Chris Pister got an idea to restart these classes at Berkeley in 2017. He started mostly very enthusiastically, but with a limited amount of success in actually taping out the chips, and students were hesitant to get into this endeavor as well. We joined forces in 2020 and started really deploying a powerful research infrastructure to help us develop these interesting chips and attract the students to it. So what has been happening in the past 5 years, shown 4 years over here, is the tremendous growth in enrollment, primarily among the undergraduate students. So the class has been developed to attract primarily undergraduate students to chip design, and the majority of these undergrads come with CS background. So at the moment, more than 90% of students are the undergraduates, and 2/3 of them have only digital circuits and systems coursework. Traditionally, chip designers are some who come with a solid device background, take analog courses, but that is not the case nowadays. Especially in our offering, we primarily target the students with CS background, and that is the majority of what we have here. So you can look at here, what is the profile of the students that we have had. So these are the total numbers, these white numbers in the end, that are all students in the class. We started with 18, and we are now limited essentially by the compute capacity and what we can teach at about 70 students in 2024. These gray numbers are undergraduates in the class. The number is now at about 60. And what you will see, interestingly here, majority of the students are juniors in the class. So what has been taped out here is that our different chips that have been designed from 2021 to 2024. And just a second, I need to quiet this dog. And we are back. So we started in 2021 with 18 students. 10 of them were graduate students, 8 of them were undergraduates, brave undergraduates who started, tried this out in TSMC 28. And then in 2022, we moved on to the Intel 16 process, designed 2 chips. In 2023, we went up to 54 students. And 2024, we had 68 students, again, designed 3 chips in the class. So, what was the magic behind this? Well, there was no magic. We do design a lot of research chips and design them fairly quickly. And we have well-developed process by our graduate students. That process essentially mimics the industry approach, but we do it in the academic environment with much less resources. Our idea is to try to design things that are modern and relevant to today, so that means that we will be designing systems on a chip. When industry designs systems on a chip, they use off-the-shelf components, and they often purchase those components. They license something from big vendors. We don't do that. We use open source components, and they're available to anybody to use. So what we offer to the students as a starter are RISC-V processor cores, a complete memory system, a network on a chip, generator, and some of the peripherals. These, in our methodology, are generators. So they're highly parameterizable pieces of software that generate instances, and students will configure them for their targets. We have an offering of Rocket, which is a RISC-V in-order core, a Boom out-of-order superscalar core, or Saturn V, which is a vector core. Network on chip generator is called the Constellation, and there is a number of other components that we call that are parts of so-called Rocket chip, which generates SoC components. We use a tool called Chipyard to generate the starting SoC, and then we modify and add various functional blocks. Students use these bare bones as a basis of a functional system and add their own components. There may be peripherals, there may be coprocessors, accelerators, or mixed signal subsystems, and they form a team of about 15 to 20 students to build a complete system on a chip. Each team of 15 to 20 students is divided into groups of 2 to 3 students, maybe sometimes 4, that work on a particular block that gets integrated into this SoC. We try to have them practice the agile design methodology where they iterate rapidly through the design, but we make sure that we arrive to a functional design at a midterm, the design that at least has some functionality, may not be complete and may not be quite clean, but use the second part or a second third or the last third of the semester to clean that up design, to test it and make sure that we get as much of a functionality as we can. This tool stack that I've mentioned is called Chipyard. We have put together this Chipyard as an organized framework for designing custom systems on a chip, or these days systems in a package. So somebody will envision this custom SoC configuration, and that will exercise these RTL generators that consist of RISC-V cores, accelerators that are commonly done by the students, multi-level caches, peripherals, and maybe some custom Verilog. It goes through the build process. In this build process, it gets translated from the native language that we use, which is Chisel, through its intermediate form, which is Fertile, to build targets that are appropriate for either FPGA simulation, software RTL simulation, FPGA prototyping, or automated VLSI flow to get us to the GDS that can be fabricated. It is completely open source. It runs anywhere, including my laptop, and it is available on GitHub, ucb/bar/chipyard. What's actually inside this Chipyard is a lot of stuff that is open primarily because of the availability of the RISC-V instruction set architecture. Hopefully many people have heard about the RISC-V. RISC-V is an open ISA. What is an ISA? ISA is essentially a contract between the software and the hardware that specifies the instruction set, and if the hardware design complies with that instruction set architecture, then any software that is on top of it that would be running correctly on that architecture. To start with, it runs Linux distributions, and as of recently, we have heard that it runs Android. It comes in various shapes and forms, RV32 to support 32-bit address spaces, 64 or even 128 address spaces. It is something that came from the need to teach many undergraduates something that is relevant. So it's a very modular ISA. The base ISA has only about 40 integer instructions that can be covered easily in a few weeks in a sophomore class that I'll mention later. But a lot of extensions provide full general purpose ISA, including floating point, vectors, and now what is being discussed as matrix extensions and many other things. It is designed really to be modular for extension and customization. It was developed by UC Berkeley, but very quickly graduated from Berkeley and is now maintained by RISC-V International. And the idea here is to try to reuse this massive software effort. When students for the first time design a RISC-V core, I can tell you that there is this huge excitement that they find out that they can essentially run any kind of a C code on their own custom core. If you're into this business, there are very few things that match that level of excitement. Now, having an open and free ISA doesn't mean that designs need to be free. There are many processor cores that have been designed in RISC-V ISA. There is a small number of them that are free and open. Most of them are commercial that people can license from big vendors. But there are some research cores that are well vetted and tested, supported by open source organizations like CHIPS Alliance and Open Hardware Group that involve this Pulpino platform and the Rocket and the Rocket chip, which is what we use in the class. So when we take a look at what is inside the Chipyard, I'll try to walk everybody through what is in there. There are these generators that are some embodiments of the architecture. So you'll find RISC-V cores, you'll find accelerators, multi-level caches, peripherals, and some custom things. When you instantiate something from the Chipyard, that would be some kind of a digital SoC template, what you may find out there are different tiles. Tiles are the basic units of repetition. In the chip, you may have a Rocket tile, what I mentioned as an in-order core, and a Boom tile as an out-of-order core. And it has a number of things that are built into it, like L1 instruction and data caches, page table walkers, such that you can implement in a complete memory system, and then links, interfaces to an on-chip bus. So, and there is a range of cores that we can that are included and reasonably tested in the Chipyard, but you can add your own, and a number of researchers and students have replaced those cores like Rocket and Boom with something that suits their needs better. Walking through the rest of the Chipyard, or what gets generated there, there are so-called tightly coupled accelerators that conform to this ROC protocol. It's a very simple protocol for where the processor core decodes an instruction, and if it is something that corresponds to the specification for the RISC-V coprocessor, it will send it to a coprocessor. Coprocessor and accelerator will execute that instruction with the data that the core has fetched, and signal back to the core that it is done. It is a relatively simple protocol that is out there. There are more complex custom accelerator processors. In this case, as I mentioned, the core decodes and sends these custom instructions to the accelerator. Accelerator writes back into core registers, or can also write it into the cache. And we have seen a number of generators that are out there. We are including a few well-curated ones and well-used ones in Chipyard that include the Gemini ML accelerator, Huacha vector accelerator, a number of other vector accelerators, and an educational SHA-3 encryption accelerator. Including accelerators as coprocessors is one way. The other way how you can add a custom accelerator is by mapping it into the memory space through MMIO. And though both of those methods are common ways how many students have in typical in computer architecture classes around the world have exercised this Chipyard. You don't touch the cores themselves. You develop an accelerator, and by including it into the SoC, you get the full system level performance. One example here of a memory mapped accelerator is NVDLA, a highly popular another machine learning accelerator from NVIDIA that has been open source. We also have example of an FFT accelerator that can be placed in memory mapped IO space. A standard bus in RISC-V rocket chip world is so-called tile-link. Tile-link looks a lot like, if people have ever seen the AXI bus or some elements of ARM's coherent protocol. It is, however, an open source. It is essentially takes a lot from its AMBA predecessors, and through a multi-level bus connects a wide range of memories and peripherals to the cores that are instantiated there. And it does have, if you would like to live in the ARM world, it has adapters to AXI4 and ARM peripheral bus. By default, Chipyard uses a crossbar to connect many of the components, but crossbars, whoever has, crossbars are the highest performance interconnects, but they do, they are physical design challenge. It's a lot easier to put these things on a network on a chip, and we have a network on a chip generator included in the Chipyard. It is called the Constellation. It is a drop-in replacement for tile-link crossbar buses. And then we have shared memory. We are grateful to a startup company, Sci5, that has opened their generator for L2 caches. And then we have models for the DRAM interfaces to external memory controller. And actually we have in development an LPDDR4 controller and PHY that at one point will open source. And then there is Chipyard has a number of these peripherals and IOs that are really necessary, and they need to be done right, but they're not that interesting to design. So what you will find in there are core level interrupts, platform level interrupts, interrupt controllers, JTAG, debug modules, boot ROM, UARTs, GPIOs, PI, I2C, PWM, and a number of other peripherals that can be included by including them as one line of a code, and a number of other useful things there. We also have UCI Express, actually fully open source digital part of the PHY. That ANSA worked on it as an undergrad, and then we also have a full analog mixed signal PHY as well. When we have the RTL, students in research and in teaching need to take that RTL and implement it translate it to GDS. Usually when you work in a company or if you're in a university, people will try to put together this kind of a tool flow that invokes a number of tools that do synthesis, place and route, and other collateral steps that translate that RTL written in Verilog or VHDL down to a correct layout that is LVS and DRC clean. And it is something that is not that easy to put together. It is something that is tailored to the tools and the technologies that are being used. And often has very different purposes. Companies do that to target one very high volume product in a particular technology with particular tools in mind. If you're in research, we are mostly scavengers, and especially in teaching, we are even more scavengers. We will use anything that is given to us, usually for free or at a very low cost. So we need to be very flexible. We need to have a flow tool that is able to combine all kinds of tools, open source and commercial, with all kinds of technologies that we can get our hands on for different kinds of designs. So we built this flow tool called Hammer that became rather popular. You see it on the link on the bottom that separates the design concerns from the tool and process technology concerns and generates these customized tickle scripts that invoke the tools from Cadence and Synopsys and open source to build the GTS. We have technology-specific plugins, those that are done for fake PDKs, and open source Skywater 130 nanometer technology are open and you can use them as a model. But this class primarily used TSMC early on and then Intel 16 plugins to design the chips. And at this point, I'll briefly pause and answer any questions that there may be over there in the chat or before I dive into the chips that have been designed. Are there any questions?
I think most of the question was answered by Bianca. So
Awesome.
yeah, like I don't think you need to pause at this moment, but yeah, audience can ask question through the Q&A during the talk as well. Yes.
Okay, I see some more questions flowing. Maybe
I think Bianca is very good at answering them.
excellent, and I'm happy to answer some of the curated questions later on.
Yeah, you have a
Okay.
good
So how does
great.
Okay, so here's how things work in a course of a 14-week, or if you add a reading week in Berkeley, how does it work within 15 weeks? So this is a spring 24 course timeline. We start with students on the first day of the semester. So a year ago, we started on January 17th. Keep in mind, none of these students have ever designed a chip. Many of them don't even know the terminology that is being used. Most of the TAs in the class are undergrads who went through this exercise once in the previous offering of the class, but some of them have been involved in research chips as well. There is really not much time to waste in this class, so we start really hard. We assign them the tutorial to learn the Chipyard on day one. And we want that to be done in a week. That tutorial is, by the way, available online, so for anybody who wants to play with it. And then we put them through this fire of 3 more labs in sequence that lead them to a toy tape out, which is a minimum instance that you will see in a little bit of something generated from Chipyard, mapped onto the RTL, and from RTL implemented as a GDS, ready for a tape out. Most of the chip is empty, but it has the core I/O, one rocket core, memory, and some of the basic peripherals. And we do want that to be ready to go about 1 month into the class. Usually when you work with Intel, who has been donating us area in the past, they require some of these mock tapeouts, TMA1s and TMA2s, 2 months in advance and 1 month in advance before the actual tapeout. And around the first mock tapeout, we really insist that students have a preliminary design freeze. It is not exactly, we have a hard time enforcing that, but after the spring break, we go through a fairly thorough and rigorous design review. People from industry joined that design review right after the spring break in early April. And then we have an actual DRC clean mock tapeout in TMA2. That is a month before the real tapeout. Last year it happened on April 11th. Not everything is in its final form there, but we have a clean design that can be submitted. It may be missing some blocks that were not quite clean and ready. Students have another 3 weeks to do that. Notably, most of the students are in the class are undergrads, so from mid-April, their other classes start contending for their time, and the activity on chip design starts to slow down towards the end of the April because other projects are due. We run a final design review during what we have in Berkeley as a reading week when there are no classes. Students finalize the design. There are final corrections if Intel complains about something in the GDS, and we taped out last year on the 10th of May. The design was sent out to the fab on around the 17th of May. So one of the big things that we have done is we have taken quite a bit of an input from our students to try to streamline more of the learnings in the lab. So we have now a set of 4 labs. Some of them have parts A and B that guide students through designing this basic skeleton of a chip. So in the first one, they go through the language chisel that we use for design capture and the Chipyard. In the lab 2, we teach them how to go through a VLSI flow with Hammer. Lab 3 adds components that are needed for custom blocks, typically analog blocks, and Lab 4 integrates everything together with a path frame to come up with the simplest possible design that is out there. So that starter design is something that has been generated in Lab 1, exercised in Lab 2 through a VLSI flow, and integrated in Lab 4. That builds a RISC-V rocket core, a cache, basic peripherals, SPI, UART, JTAG, and very importantly, adds Intel-provided GPIO for flip chip packaging. We do that. Intel was very nice to provide that I/O. Otherwise, we would have spent the rest of the semester attempting to route to these bumps in the package. We target 2mm by 2mm dies that are at the end of this exercise mostly empty, and they're going to be populated by the student designs. So here is how it looks like pictorially. On the left-hand side, we see what comes out of this Lab 4 template project. You'll see a RISC-V core, a little bit of a memory, phase lock loop that is used for clock generation, and GPIO around the periphery of the chip. Everything else over here is just basically a dummy fill. It is there to be populated with useful stuff. At the end of the class, we end up with 3 very differentiated chips, 2 chips that are mostly digital, and 1 that is mixed signal that has a digital component and a radio on the left. So enough of that. So what are these chips that we have designed? And that's what I'm going to talk about for the next approximately half an hour. In 2021, we designed something that is OSCI Bear and has been actually widely circulated out there through a Solid State Circuits magazine publication. In 2022, there were 2 chips In 23 and 24, there were 4 chips. So what I'm going to talk about is essentially the content of these chips, and a lot of the material there is available to be replicated. So in spring 2021, remember this was pandemic. Spring 2020 was particularly, there was an attempt to run this, but there was no way to tape out with the disruption of the pandemic. But in spring 2021, we decided to make these tape outs work. We decided a new Chipyard to use a new Chipyard based flow, and we got 18 very dedicated students who had nothing else to do because they were in a lockdown anyway, designed these chips. So we had 10 graduate students and 8 undergraduates. Early on, there was a delay with signing the necessary NDAs for TSMC 28. So we essentially lost 2 weeks. So the whole cycle was a 13-week cycle. And there were 3 instructors and 2 graduate student instructors that spent a lot of time making this work. What was in that chip was, on the right-hand side was a CPU. It's a digital block. Was a rocket chip that had 2 custom components added by the students. On top was an AES accelerator for crypto. On the bottom was a digital baseband for a Bluetooth low energy. The idea here was to build a micromote that is a self-contained, that has a CPU, encryption, and a digital baseband, together with a complete RF to build a Bluetooth low energy mote in the class. In order to speed these things up, some of the components were, as I mentioned before, provided by the Chipyard. We have also given students an automatically generated SAR ADC to use in the baseband of the Bluetooth low energy transceiver. They managed to tape this out. It was 1 millimeter by 1 millimeter chip in TSMC 28. We paid $10,000 for fabricating that from Muse, and the money was donated for that fabrication was donated by Apple. Overall, really good investment from Apple because of all of those students. I think all but 1 undergraduate ended up at Apple, along with a few graduate students. This is something that made the Berkeley Engineering news early on, and there was an extended Solid State Circuits magazine article on what was in it. Also, the paper was published was actually published and demonstrated as a Hot Chips. And if you haven't been to Hot Chips is one of the premier Computer Society, or Computer Society's premier conference, with a lot of big products get announced, and we showed some of our chips over there. So here is an example of an amazing functionality that has been achieved with this chip, in the sense that the transmitter was able to send Bluetooth packets that were picked up by a commercial Bluetooth part from Nordic. One thing that we didn't show is the receiver was not as functional, so we could not receive. But this is nevertheless quite impressive. So take a look at this demo. And although we practiced it, the audio is not coming through. But what you can see is essentially a demonstration of this chip compiling packets, and with the the FPGA doesn't do anything. It just essentially helps the chip boot. What you see here is a programming of a test chip that takes a little while, eventually sending a hello world packet to the world, and then Wireshark on the received end receives the packets and decodes them to decode the message that was sent via Bluetooth that says ASCII Bear. That was the name of the chip. ASCII is, this is a play on the words with the name of Berkeley's sports mascot, ASCII. ASCII Bear says hello. All right. So with that success, the word spread out among the students. The course became, students are still, you can imagine this from the world of undergrads who are looking at this and are we really going to design this chip in one semester? The course became a lot more popular, so we had a number of juniors now signed up together with seniors, with a smaller number of PhD students, and the same instructors designed these chips. A monkey wrench was thrown our way in the fall of 2021 when TSMC temporarily had to export control their technologies, including the 28, and we had to switch that technology to Intel. Intel came forward actually with a donation of the test chips in their 16 nanometer class technology. Now keep in mind, 16 nanometer technology is a FinFET technology. It has more complicated design rules. It is a little bit more challenging, or significantly more challenging to get to a design closure in that process than is in TSMC 28. But nevertheless, we had a success. The chips here on the left-hand side, we have another version of a SCUM, the chip that we have seen being designed in TSMC 28 in the previous year. That had a RISC-V core, Bluetooth Low Energy. This time it had an added support for 802.15.4, like a ZigBee baseband. With the same RF front end, low dropout oscillators and the references, such that it is more self-constrained. On the right-hand side, we have barely ML, the first iteration of the play of word on a machine learning accelerator. It had 5 RISC-V cores that had 4 rocket cores with custom sparse matrix accelerator, not fully functional Saturn V vector processor, and a NOC. Here is that was also presented as a poster in Hot Chips 23. So our students put together quite a bit of a show when going to Hot Chips, because every time we have an exciting demo, some of those you're going to see here. And Hot Chips has a lot of attendees, so a few hundred people stop by our posters to see these chips. So here is essentially what it is. I've shown this before. There are several processor cores that are in here, connected to a NOC, to the memory system and the peripherals, with some custom accelerators added to each of these, to each of the processor cores. When looking at what was in there, so one big thing was what was a custom design was the machine learning inference tile that was capable of running of fairly high throughput of about 4 gigaops to run machine learning inference. What students have demonstrated here was ability to run MNIST inference, and that was the hot chips demo. Now, that was a success. Now in spring 23, the course became even more popular among the students. So Lucy was in the year before, Ethan and Ansa, Ethan was in, Ansa was in the spring 23, Ethan was in spring 24 offering of the class. Now the class was, even more undergraduates, mostly juniors this time, and we designed 3 2mm by 2mm chips. There was a new iteration on a barely ML chip, machine learning chip. There was another digital chip, that mostly digital chip that was doing signal processing for robotics, and another iteration on the Bluetooth low energy chip. These chips were designed to really offer full functionality and run full benchmarks, actually premeditated, thought through in advance. What would it take to run machine learning inference on some kind of a chip like this? So there were 4 RISC-V rocket cores, and each one of them had some kind of a student design accelerator. These are sparse matrix accelerators. We had one variant in 2 cores and another variant in 2 other cores. Also, it implemented had dense matrix computation next to the L2 cache banks, where there was a simple arithmetic for dense matrix multiplications implemented right next to the L2 cache banks, that was accessible by a DMA, and was able to perform this near memory computation. So somebody who is trying to run a machine learning application would try to map this application to a combination of dense matrix operations near the memory and sparse matrix operations that were near the core. Dense matrix stuff near memory worked fine, but the sparse accelerators had quite a few of the issues, and in most of the demos were not used. If you look at how did the layout look like, it now in 23 converged to more of a template that we have been pursuing for a while. The RISC-V cores are sitting with their custom accelerators, sparse matrix accelerators were sitting in the top of the die. The memory banks with near memory compute were at the bottom. There was a scratch pad that all students will always tell us that 64 kilobytes is not enough. And Intel provided PLL was sitting to the left. Around it was the I/O that was pre-routed by Intel, and we just connected to that I/O. The other chip that was mostly digital was designed for running both ML and robotics applications. So we had a few custom accelerators that were added to that. Common filter, linear quadratic regulator accelerator, both types of vector accelerators. There was one student very ambitiously did a RISC-V boom core, where she added a memory tagging extension, her own proposal for a memory tagging extension, security extension that exists in ARM but does not exist in RISC-V. And then, there was also a mixed signal component, which was a switch capacitor DC-DC regulator. It conformed to a similar template that we had, so there was quite a bit of a reuse between the physical designs of the 2 chips. Again, the rocket tiles and the boom tile with MTE were sitting on the top. memory banks were sitting at the bottom, PLL was sitting on the left, and the scratch pad was sitting on the right, and in between was the NOC, the fabric that connected all of that. Of course, the IOs were placed in the same way as what we have seen before. Now, these single chip micromodes have a little bit of a different of a layout because of a large number of analog components that exist on them. They didn't conform to the same template, not in 2023. So they had more of a custom pinout, or they went on a more of a custom package. So what you will find in there on the right-hand side is the digital stuff that had a 32-bit RISC-V core with crypto accelerators, radio that is now fully functional, Bluetooth, ZigBee radio, and microvolt precision ADC. On the left-hand side, you have power for powering all of that. There was a research radar transmitter that was running at 90 gigahertz, a number of on-chip generated clocks, and a radio that was a crystal-free 2.4 gigahertz transceiver. Notice that all the graduate students that were in the class, most of them were the ones that were working on the radio here. One of the things that we added in 2023 were these FPGA boards that were donated by Intel that could fit the entire RTL for a digital chip, and we tested them pre-tape out, where our target SoC was sitting on one of the chips, and it was exercised by on one of the FPGAs, and was exercised by the other FPGA to check the functionality. The way, one of the things here, what we did also in 2023, we worked together with our friends from Morgan State University that mimicked our design flow but lagged by about a week. So they created a 4-chip that went together with us. And the way how these things work is Intel usually puts things on a 4mm by a 4mm. That's a minimum unit that they fabricate, but we subdivide that into 4 2mm by 2mm chips. So our Berkeley chips were sitting in 3 quadrants of that 4mm by 4mm die, and Morgan State chips was sitting in the 4th quadrant of that die. The chips, looking at what was happening in the fall 23, the chips are in the fab. They went to the fab, as I said, on around the 17th of May. They're cooking throughout the summer in Intel's fab, but our semester starts on August 23rd. We commenced immediately. What we do is half of this class that does the bring up are the students who have designed the chip. So we have about 25 students in the bring up class. Half of them are the ones that designed the chip. Many of the juniors come back to design their chips, but seniors are gone. Seniors now have jobs at Apple, Intel, and other companies. And new students sign up who are very curious about what the previous class has taped out, and they participate in the board design and bring up and testing. So in some cases, we use the Intel provided boards. In some cases, especially in the fall 2024, we designed a number of our own custom boards. So what the class does first, they design the boards, they get them ready. The chips show up typically in the late October. In fall 23, they came on November the 5th. And amazingly, just 2 days later, students managed to, through low-level programming, communicate with some of the serial interfaces on the chip. 2 weeks later, they got development environment to work and compile the C code and put it on a scratch pad. And then things slow down because there is Thanksgiving and there are finals, but they don't give up. On December 19th, they got the external DRAM working and Linux booted on some of the digital chips. And then in January, ran a number of demos. For many of the bring-ups, we use this large FPGA. So what you see here, the test chip is sitting underneath this ironwood socket. It is torqued inside. There is a board, in this case designed by Intel Labs for testing the chip. In some cases, there is our custom PCB. And on the right-hand side, there is an Agilex FPGA that is used for exercising the chip, and it's connected via internet and Ethernet to the real world, to the terminals. So the things that was simulated in the spring was a copy of an RTL image of this chip exercised by this FPGA. And then we replace that FPGA by the actual chip and test it with the other FPGA that is in here. So what was demonstrated in 23 was also demonstrated at Hot Chips 24, was an ability to run a small llama model trained on tiny stories dataset. This is quite impressive, and you're going to see that a little bit later. How does barely ML24 does that? Essentially, this is a neural net that is a version of Microsoft's Tiny Stories, where it runs through essentially dense and sparse linear algebra based on a prompt, tell me a story, comes up with a story and prints it out on the terminal. The stories are mostly appropriate. Sometimes they're sad. You never know what language models will produce for us. RoboChip was also showing large amounts of functionality, and it was shown to be in a live demo to control an inverted pendulum. So, and the video is not showing up over here. Student whacking this inverted pendulum and getting it to stabilize. In Spring 24, this is a mistake. We had 68 students, actually, mostly undergraduates, and they designed, again, 3 different chips, another version of an ML chip. Then we had a RoboChip. I think I needed to update these, but anyways, I'll jump into this. So there was a SCAM4 version that had new features, new analog front end that was actually functional. These analog front ends don't always work, and then a well-tested rest of a front end. Barely ML had a number of new accelerators that were added to it, in addition to the dense and sparse linear algebra accelerators. So it had a quantized transformer, a convolution engine, supported things that were buggy previously, and so on. A new chip was this signal processor that was optimized for signal processing applications that included things like text-to-speech, because it would be nice if this llama story was actually narrated by voice. It was able to do sound recognition, and had a number of accelerators that included the FFT, a convolution accelerator, and a custom written audio interface through I2S and Signal Delta ADC that is able to work with the rest of the world. So every fall, chips are brought up by the students who designed the chips and those that didn't. One of the new things that we have developed last fall are really well-guided labs that cover both the PCB design and low-level programming that is necessary to bring up the chip. Guide students through the FPGAs and the basic interfaces for functionality. ideally, we would like to demonstrate something like this. And hopefully this audio is going to come through. The hope is to design an audio is not coming through that 3D printed replica of me is it just totally, this Bora bot totally looks like me, would be narrating with my voice that story. I'll pause here for a second.
So Bora,
and
we had
perhaps
one
switch.
question. Yeah, Bora, we had one question that needed kind of a response from you. Someone was asking to learn more about the Apple Silicon Initiative.
The best Apple New Silicon Initiative is they have started that in a number of universities where they provided some funding. They provided guest lectures to start these kind of tape-out classes. We were in the pilot of that, and we are now in the 4th year of it. The best, you can search on the internet Apple's New Silicon Initiative and see if you can get connected with them. There are a few features in the Solid State Circuits magazine from recently from UCLA and Columbia that also mentioned Apple New Silicon Initiative, and there is a new thing if you're in the US that is being done with NADCAS, the CHIPS Act money that Apple has partnered with. But I'm going to pause here and answer a few questions and give an opportunity for a current 2024 class chip demo by Lucy and Ethan.
So if you have a question, feel free to type it in the chat window while we transition to Lucy and Ethan.
It's a pleasure. It's a pleasure to meet you all. And just to make sure, how much time do we have? Just
You have some time.
to make sure we're respectful.
Yeah, go ahead.
We have a 2-hour slot, but we do not want to use the entire 2-hour slot.
So you have plenty of time. So go ahead.
Okay, got it. Thank you.
All right,
thank
you.
Yeah. In that case, yeah, let's introduce ourselves real quick once more. So
So, hello, I'm Ethan Gao. I'm a 4th-year undergrad, and I've been through this whole, been in the Silicon pipeline that Bora's been talking about basically my entire undergrad. I joined the bring-up class in my semester, my 3rd year. Took the tape-out class the year after, and kind of been stuck since. So I've ended up TAing last semester's bring-up class with Lucy over here, and this semester I'm TAing the bring-up class to help this year's chip be even better.
it's a pleasure to meet you. So as Ethan mentioned, my name is Lucy. I was an undergrad here as well, and I took part in the spring 2023 iteration of tape out that Bora mentioned. After which, Ethan and I went through the spring 23 bring up iteration and taught the spring 2024 bring up course. Spent way too many nights and days at the lab, but ended up having a lot of fun. And today we would like to show you one of the chips from that spring 2024 tape-out class, and then some demos that we worked on during the fall 2024 bring-up class. And when we say we mean all of the students. So this is an effort of many, many folks. But yeah, let's pass it off to Ethan to guide us through some of the setup that we did.
Yeah. So one of the first things that we wanted to
Can we
work
pin
on
the
before
video?
the chips even came back was a set of PCBs for us to be able to use and test these chips. While for the digital chips, Intel does provide the headlight platform that Bora mentioned. This is suboptimal for the types of chips that we like to design, which have lots of I/O and are designed to be able to have rich I/O and can interface with lots of peripherals. Since this breaks up most of the pins to an FPGA, which is great for testing, but less cool if you want to do interesting demos. So for the digital chips, we decided to do a three board system. So the first board that we designed was a little SAW module over here, which takes the chip with all 4 of our quadrants and breaks out all the pins to these small board-to-board connectors and provides clocking to each quadrant of the chip to simplify design of the other boards. These little SAW modules plug into breakout boards like these. So these boards provide power to the chip and connect to those board connectors for various tasks. And these are specialized for all different sorts of different demos. For example, this board over here is designed to just break out all the IOs to pin headers for easy prototyping. And this board over here is designed for running Linux and has a bunch of built-in peripherals on board for things like Ethernet, USB, and SD card. All these boards have an FMC connector, and these connect to an FPGA for expanded capabilities.
Okay, so thank you, Ethan, for explaining some of the pieces that go into our setups. We're going to show you now how they fit into the demo that we'll be showing you today. So yes, right here, if you can see right in this area, we have the bring up setup that we're going to show you. You see our Spring 2023 chips on the quadrants of the Intel package silicon here, on the student design SOM, on top of one of the PCBs designed for general purpose demos and data collection, which is what Ethan showed you earlier. We're again using the DataStorm FPGA for bring up. Particularly right now, this is for external memory. So don't worry, the actual compute is being done on chip. This is a real demo, we promise. And the chip is running at 500 megahertz via PLL from the FPGA clock, which you'll see will be important. We use this setup to introduce students to the Quartus toolchain, kind of teach students how to write bare metal code. So someone was asking about bare metal IDE. That's our set of software libraries that students learn how to use and then also write additional drivers for PWM and so forth. In addition, we use this to debug using both our research Thailand infrastructure and industry standard JTAG and so forth. And we also use this setup and also the Agilex setup right here in order to do emulation and in order to do demos that have higher LUT and memory requirements. So larger models, or sometimes we want to emulate the whole SoC. For example, it takes a few weeks to actually get the silicon back at the beginning of the bring up class. So we've been trying to develop this infrastructure with the students to make this process easier. You'll notice two wires that hopefully aren't too ugly sticking out of this board, red and black, and that's because this SOM has been modified in order to take in external power for our SHMU plot demo. So that's going to be one of the things we'll show you. In particular, you can see our Keithley SMU right here, which is pretty fancy. And then we have a Python notebook that allows us to see if it's, yeah, I think it's, I'll just scroll up to the top. So you can see it's a real notebook, again, not just screenshots. This is actually what we're using. So you can see here we have a Python notebook that allows us with just a few clicks to automate a lot of characterization of the chip's electrical qualities across different corners. And we'll show you this again in a second once we're actually showing what the workload looks like. But yeah, this is how we can sweep and characterize, and they will show it to you in a second. But we want to first zoom in back on the chip and on the workload we're going to be showing you today. So I'll pass it off to Ethan.
Yeah. So the chip that we're going to be working on today is a DSP24 chip, which, as Bora mentioned, it's been optimized for audio processing tasks and has a whole bunch of peripherals and accelerators for that. However, in addition to those, it also has four wide RISC-V compliant Saturn vector cores, which means that it's also great for running machine learning applications as well as the Barely chip. So in this case, this chip right here is going to be running a small large language model called Tiny Stories, which is based on the Llama architecture and llama2.c file by Carpathy. So if I go to this laptop over here, we can see that we're using so in order to program the chip, we program and use it and program the chip, we're using all industry standard tools. So we're using GCC to build the program, OpenOCD to connect to the chip, and GDB to debug it. For those who don't know, OpenOCD basically abstracts away all the details of actually talking to all the level of commands to talk to every individual chip, which GDB can then connect to in order to give you full debug access like you would expect in software world. So you have full debug ability to set breakpoints, run different programs, inspect registers, and modify code on the fly, which can be incredibly useful, especially if you're debugging under verified accelerators in IP, like we sometimes are in the bring up class.
That's too true, too true. And we've been talking a little quickly, I realized, but yeah, you can see on screen right now the setup for the Llama demo.
Yeah. So what we're doing right now is we're just loading in the program that we're loading in the compiled Llama binary, and all this does is it configures the PLL to take the 50 megahertz it's getting from the actual board and bumps it up to 500 megahertz and starts inferencing. So if I type run right here, and I open up a serial console that's hooked up to the UART of the chip, we can see that it's actually inferencing a story. And if we give it a moment, it'll start. You can see in all its incoherent glory, mostly coherent glory.
It's mostly coherent. It's gotten better. We've been trying to do this demo for multiple years now, and it's gotten better every year.
Yeah, and we've been experimenting with larger, more complicated models, including fine tuning. So right now the inference speed might seem a little bit pokey for 500 megahertz, and this is mostly just due to memory bandwidth constraints, since this current setup is running a lower bus frequency just for testing purposes, and testing stability purposes. Though we're currently working on pumping that as far as it'll go.
Yeah, let's keep that running in the background while we talk about the rest. So let's transition to the shmoo-plot demo. So say you're running this workload and you really want to characterize it a bit further to see how much power are you actually consuming when you're generating your tokens, when you're running the Llama model. And the shmoo-plot allows us to do that. So you can see here, again, that Python notebook that we were talking about before. Sadly, we can't screen share from this device, but we will transition our camera duties. So I'll go through really quickly how this works, and you see that it's pretty well automated. So it's actually a pretty short demo. You're not going to sit here for an hour and watch us take measurements. So we have some generic imports for a Skippy library, as well as some additional code that we had students write. We connect to the SMU, set some basic settings like the start voltage, end voltage, start clock and end clock. So this is pretty standard things that you would also see in industry silicon validation setups, which is a pretty helpful learning experience for students. Because we're responsible engineers, we set current and voltage limits and we set buffers and so forth. And you can see an example run here for an older measurement at 50 megahertz. But we don't want to show you an existing measurement, we want to show you live data collection. So here right now, you can see power without workload with the core spinning idle. We can consider that idle power at 50 megahertz, which is the default input clock rate. But we want to see how this differs when we're actually running the Llama workload, which is running right now, and how that workload looks like in terms of power consumption. So again, with just a simple click, we see that we're getting a very different power characteristic, which is pretty interesting. So you see here it goes up to around 59 milliwatts. And we're very curious in seeing how these power spikes might be correlated to attention iteration. So how with every iteration of running attention, we might be getting power spikes. Again, a pretty short demo because we can run it with one click, which is really great because we've been able to automate a lot of the kind of laborious data collection across voltage, frequency corners, and use this in research and publications, as Bora mentioned, which is really exciting, especially for a class chip. So yeah, you can see Shmoo here, and then Llama still on your screen. And feel free to ask us any questions. We went through things very quickly, but Ethan and I are both very happy to talk about bringing up tape out, the student experience or the teaching experience, anything else you would like.
So there is a question, Lucy, in the chat. Would the Python notebooks to sweep and characterize the test chips be the same as those for verifying their IC designs for the SoC design course in the spring semester?
All right.
I'll take that one.
Okay.
There would be.
We see the comments in the chat.
Custom design.
Thank you.
these are custom designed for essentially characterizing the chip. They're not
Oh,
the
I see.
same
Oh.
as what was used for characterizing the chip during the tape out. It is, there are research efforts right now to try to get the dynamic profiling of SoC performance. But what I want to say here is it is rather brave to run these kind of demos live, and I do.
That was
want to
excellent.
applaud
It
one
was
more
really well
time.
done. Thank you.
Oh yeah, and we see
especially
some
in the-
oh, sorry. Yeah, we see some
So, yeah,
questions in
anyway.
the Q&A too.
Yeah.
Okay, but
I think they
don't
got
hear
answered,
us,
Lucy. I think they got answered.
Okay, so a few more comments here. So especially in the light when people go to these kinds of conferences these days, like ISSCC, when there is a lot of questions about whether the results are reproducible, we do very strongly encourage our students to show that in a demo. Now, the question for the Solid State Circuit Society young professionals and women in circuits question maybe, how do you get started to get this motivated in this area? Most of our materials are open, so you can learn, you can follow along. Most of the entry point is essentially through the Introduction to Computer Architecture and RISC-V 61C class. It is at on the website cs61c.org, and we put a bunch of videos, that we recorded in fall of 2020 during pandemic when we had nothing else to do, and they're well curated, I would say, materials that are out there. I'll pause it here. I'm not going to go through the entire videos, but they are there, and you can see how you can build a RISC-V 32-bit processor that runs integer instructions. The one step before you get into a tape out is to learn digital design. We put our Introduction to Digital Design class also on the web. Lectures are not on the web because they're not ADA compliant, but ASIC, associated ASIC and FPGA labs are on the GitHub. Go over there and you can replicate it. Especially if you're in the field of circuits, you may very much appreciate our labs that are based on open source SkyWater 130 nanometer technology. Students in, again, that class during that 14-week semester create a layout of typically their RISC-V core and some of the peripherals running some kind of an application, but they don't send it out for fabrication. We are doing something very new. Lucy and Elam Day Friedland are the student coordinators for that pretty crazy class. It's a student-run class launched in fall 2024. When they take their digital projects that they designed in the class that had these, like mock designs, and actually tape them out in SkyWater 130 nanometer process. We got some funding from the government through the Microelectronics Commons, and that's what they have been doing. They had a first successful tape out on November 11, 2024. And the website is here. So it's a 151 tape out class that is a light version of what you have seen now. So this is doing in a less sophisticated technology, SkyWater 130, but it is completely a student-run class, and they put out the materials that you can follow. Somebody needs to provide funding. So one of these chips each of these chips are $10,000. So somebody needs to get these $10,000. We're grateful to the US government for providing those $10,000 per chip. And we have a larger number of students who are, again, jumping into that class as well, and we'll try to continue going. if you're interested in Chipyard for both teaching and research, there is quite a bit of a documentation. There is an effort now, since it has growing popularity, to keep adding to that, and students are adding more to that documentation. There is a mailing list. It is open sourced, everything except the things that are very proprietary to the technology, and there are many forks, many stars for the Chipyard project, and there are many publications that use Chipyard, and it became essentially something like a default artifact evaluation tool in computer architecture community, also in many of the government programs. With that, I'll wrap it up. I was not the only one that was doing this. My co-instructors were Chris Peter and Ali Nikolic, mostly dealing with the analog parts of the project that I have not talked about. It would be great to invite them to talk about the analog stuff. The class is ongoing at the moment with 3 instructors, Junchar Chen, Chris Peter, and Vikram Jain. We had about 50 TAs go through this after successfully completing projects, along with several hundred students. We are doing our best to help refresh the engineering design community, IC design community. We are grateful for Apple that helped us. Intel University Shuttle Program. We got some money from the SCALE program through Purdue, and a lot of encouragement and help from research centers that we have had, PWRC, SLICE, a number of students, and the member companies. And I can answer a few more questions, or we can share experiences. We haven't heard from Ansa Schmolbach, who graduated from here, and can tell you that hasn't had a hard time finding a grad school that would take her.
Okay, so thank you, Bora, and students. Great demo. I think we got a lot of positive comments. Everybody's loving the demo. So thank you so much for doing that live. It's great. So I think there's a couple of questions here. Would Professor Bora or other instructors offer a similar course for hardware, software co-design, system technology, co-optimization, to try implementing functional models such as large work? So they want another course at Berkeley. I don't know if you have the bandwidth, Bora. And then
we are operating beyond our capacity.
Yeah.
At the moment.
Okay, and then I think there's a very specific technical question here. Oh, it's already answered by Ethan, so that's okay. What happened to the EE141 course at Berkeley? Don't they do digital ICs in that course?
Oh, 141 has merged with one, remember that was in one of the introductory slides, our enrollments in the 2 digital classes, one E141 and CS150 dwindled down. So they ended up being merged, and they're now renamed as EX151, but the enrollments are exploding, and we need to figure out how to reconfigure ourselves to offer more.
So one of the things that I want to point out is that there is all this material out there for Skywater 130. So if you are not in the United States, or you don't have access to, some other technology, and you want to use Skywater, and you want to go through this, even outside of a course, there is a tape out contest that SSCS has every year. It's called the PICO program. Boris Merman initiated that, and they also use Skywater. So you may be able to take advantage of some of the collaterals that Berkeley has put out there through this effort, and use those in designing chips and submitting it to the PICO program. So please take a look at that. Any other questions from folks? Okay. All right.
For some reason,
we're
I
getting a
don't see the
request for
questions
SSCS
coming.
to organize a machine learning hardware accelerator contest. Lucy, you want to help?
Yes.
Just to add,
Lucy has quite a few things to do.
I know. Just joking. We will look into that. We will look
And-
into that. We're
we'll-
trying to
we'll-
do
we'll-
more for students, so we are going to look into how do we do kind of like a chipathon at one of the big conferences. So definitely we are looking at that. And if you want to give us more insight on what students need and what they want, please contact me or contact SSCS, and we are putting a very comprehensive program together for students in the next 6 months or so.
And keep in mind that Lucy may be looking for employment after completing her master's. Ethan is interested in grad school.
Lucy, talk to Harrison.
Lucy may come back.
Yeah, Lucy, talk to Harrison.
Very good. Okay.
Okay, all right. Thanks very much. It's been a really, great webinar, and I think the live demo and Hansa has been on top of all the questions. So thank you for making our life really easy. And then Lucy and Ethan, thank you so much, and Bora, many thanks for doing this on fairly short notice. So thank you very much.
Thank you for letting us, we have done, I think, quite a bit of stuff to the maturity that we can live demo it, but not very many people have seen it. We would love to get more use and more people try to try to do something similar.
Well, you had over 100 people watch it, so there you go.
Thank you.
It was a great demo. Thank you, and great lectures.
thanks everybody. Have a great day.
Thank you.
Bye.
Bye-bye.